who will be talking about sparsification in different contexts.
Great. Thanks, Arthur, and thanks to Sanjeev and Sohail and the other organizers for this wonderful workshop where I've been learning a lot. Sparsification is not really my domain over here, and graph simplification is definitely not something that I do on a normal basis. And today's talk is going to be sort of trying to take that as a point, a tangent point to go somewhere else. So I'll try to talk about sparsification applied to codes and come back to a little bit about hypergraphs maybe. So just a little bit of a broader context, even though, I mean, most of you are probably more experts on sparsification than I am. It is interesting to see where it sort of lies in the space of, kinds of things that you might do to compress data. And the ultimate object would be a compressor, which is something where you start with some data, you compress it, it's much smaller, but then from this you can recover the entire original data. And we have seen compression applied to various concepts, and it has some success, but typically you only get compression down by a linear factor, a constant factor to the length of the string x. So this is a useful concept, but it's only going to compress your information by a small amount. If you really want to compress super strongly, then the usual way the information theorists would think about it is that you should think about lossy compression, where you recover an object which is not exactly x, but something which is close enough to x. For simplicity, you might say, oh, let's say something close in Hamming distance. And then what we are able to say is at the end of this, I can, for instance, ask questions like, what is one coordinate of x? And for most coordinates, I'll get the right answer. But for many coordinates, I will not. So it preserves at most polynomially many queries, but not all of them, most of them. Sparsification as an object that we have encountered, and we'll talk about it a little bit more later, for some restricts our attention and sort of focuses on a certain class of queries, and then says, if these are real valued queries, positive real valued queries, then you say that, look, I should be able to start with some string x, compress it in some form, we call this a sparsification of x, such that for every query in our class, we are able to answer it to within a 1 plus or minus epsilon factor. So that's quite a nice different set of guarantees. And then the question is, oh, can you actually do this interestingly for anything? And of course, we are all here and we know about the Benczur Karger sparsifier for graphs. A graph on n vertices typically would require n squared bits to represent, but we know we can always compress it down to roughly O tilde of n bits. And there are no model assumptions. The only thing is the information that you get from it is not everything you want to know about the graph, but only information about the cuts in the graph. For every cut, roughly how many edges are crossing the cut. And we will talk about this extensively later, but just a quick reminder that in case you don't remember all of these things or you haven't seen this before, a key ingredient in this object in sparsification is Karger's cut counting bound, which says that the number of cuts which are small in a graph is sort of polynomially, there are only polynomially many small cuts in a graph. And as a result of this, somehow you're able to show that random sampling of edges done right work. We can ask the question, what else can be sparsified? And given this sort of context that I put to sparsification, when we say what else, you should ask the question, what is the structure of the data? And what is the information about this data that you want to recover? So it should be, what is the data and what's the set of queries? And we have seen examples of these kinds of things. Graph Laplacians can be sparsified with respect to quadratic form queries. Hypergraphs can be sparsified with respect to cut queries, where cut will say how many edges are cut, which means have at least one vertex on each side of the bipartition. And even some objects like SAT can be sparsified. I give you a SAT formula and I ask the question, compress this formula, take a subset of clauses, such that for every assignment, you can tell me roughly how many clauses were satisfied in the original thing. So these are things that we have explored before. And a very nice general context was presented for this by Roby with Kogan, which said that, look, we could be talking about this in the general context of constraint satisfaction problems. I give you some predicate In the case of SAT, it is the OR of 3 literals. In the case of regular graph, it is the XOR of 2 binary variables. In the case of a hypergraph, it is sort of not all equal sat on certain number of Boolean variables. And all of these are questions that you can ask. And it's even more nice in the sense that, well, with a hypergraph, why would you want to say that an edge is cut only if there's at least one vertex on each side? You could say maybe an edge is cut if it has exactly equal number of vertices on both sides. That's a form of a hypergraph sparsification that you may be interested in that would be captured by an appropriate predicate P over here. So you can study a whole slew of questions under this umbrella. And now the question is, for which P's are constraint satisfaction problems sparsifiable, and how well, maybe? So these are the kinds of questions that we will be touching upon in this talk. One particular class of questions that may be interesting is, well, the data is Boolean variables, some vector of Boolean variables, and I give you a collection of XOR constraints, saying the XOR of these subset of variables should be 0, and the XOR of these subset of variables should be 1, etc., etc. Now you can ask the question, for each assignment, how many constraints are satisfied? This was an example of a problem where we didn't know how well it could be sparsified before, and now we know exactly the answer for this. All right, so in this talk, what we'll talk about is something called code sparsification. Now, this is a question that was never asked before, but let me explain to you what it looks like on this picture that I have. A code is given by a matrix over some finite field. Today, for simplicity, we can just work with F2 as the illustrative example. One application will work with something else. This is some 0-1 matrix. We are doing all arithmetic modulo 2. It's a very tall but thin matrix, and the code that it generates is you try all possible k-bit vectors over here and look at all the strings that you get. That is the code that we have. And what we would like to do is to pull out some subset of these rows, maybe some order of k-ish. Whoops, did I do something? Okay. So did I, maybe we want to pick some O tilde of k of these rows and give them appropriate weights so that I can ask for each one of these code words roughly so this is, by the way, the image of the entire map. You try out all the possible 2 to the k vectors, you get the entire code, it's all sitting here. We'd like to say, when I look at this subset of the things, the weight here, the number of zeros and non-zeros, roughly is proportional to the number of zeros and non-zeros on the whole thing. And I'd like this to happen to every one of these code words that's here. Okay, this is this concept that we are calling code sparsification. And so here the queries that we are looking at are, I tell you which code word, which is equivalent to specifying this tiny vector, the message. What I'd like to know is how many zeros and non-zeros are there in the resulting word. And I'd like to infer that information by just remembering, just knowing what happens on this particular subset of coordinates. Does this make sense? Any questions? Yes?
You're not concerned about the distance of the sparsified code in any sense?
I'm not concerned about the distance of the sparsified code. It's a great question. So whenever we deal with error correcting codes, we'd like them to have large distance. It turns out for sparsification, a code of large distance is sort of very easy to sparsify. So if you just pick a random subset of the coordinates, it'll just sparsify it very naturally. So if you start with a code which already has good distance, sparsification is trivial. And the interesting examples come when the code is not a good error correcting code by coding theory measures, which is the reason why coding theorists would not have considered this question. And of course, graph theorists would not consider this question because it's about codes. But as it turns out, it is a generalization of both graph and hypergraph sparsification. For graphs, it's fairly simple to see this. If you just take the incidence matrix of a graph over here as the generator matrix, these vectors are just sort of, these are the coordinates of this code are the edges of the code. And the coordinate is 1 in a code word if that each one of these things corresponds to a cut in the graph. And this is the incidence vector of which edges cross the cut and which ones do not. So you're just capturing that problem completely naturally. It turns out also the standard hypergraph sparsification can easily be expressed this way, and I'll come back to it later. And so this can be considered a motivation for this problem. And it turns out that if you start studying code sparsification, you start getting lots of interesting results about CSP sparsification as well. So another motivation to study this question. So here are some theorems that we prove. Oh, by the way, I should have mentioned that this is all joint work with Louis Petterman, who's here, and Sanjeev Khanna. And here are the theorems that we have in our 2 works on the subject. Every linear code actually can be sparsified to roughly, so the right way to think about this theorem over here is that the number of coordinates that you want to pick over here in the sampler is roughly k, O tilde of k. Okay, so your code can be arbitrarily large as you want, but roughly linear number of coordinates are sufficient to sparsify every code. And so in particular, as soon as you see this theorem, so up to polylog factors, we are getting the Benczur-Karger result.
So what is n? Is little n capital N?
Oh, sorry. Yeah, this little n is the same as that capital N there. I mean, yeah, sorry. In coding theory, language n and k are sacrosanct, whereas the n in graph theory is a completely different n. So this is going to lead to some confusion. These results extend from just finite field kind of objects to you can start thinking about any linear map from integer vectors to some abelian group, and all of these can be sparsified. This becomes interesting in some CSP contexts. And in fact, there's a final theorem which talks about nonlinear functions. Both these theorems are about linear maps and linear maps. And this is a higher degree polynomial map. This statement also tells us how to get sparsifications. These are when you have nonlinear sized sparsifications. If you can only sparsify to length, some graph, maybe hypergraphs can, some problems may only be sparsifiable to n cubed in the number of vertices n. Well, those are explained by these. And as far as CSP sparsification is concerned, this theorem gives us near optimal results for every CSP that I know of so far.
I'm sorry, I did not see it very transparently. You said that theorem 1 already implies the Benczur-Karger result. Could you just explain it once more?
Sure, yeah. So the blue part of the theorem implies that. What it says is that if I'm given a graph, any code, then sampling roughly O tilde of these rows is sufficient for me to capture the weight distribution that I'm getting here. That means for every cut, I will be telling you roughly how many edges are crossing the cut. And then in order to describe this matrix to you, I don't need to give you, I mean, each one of these matrices has just 2 ones in every row, right? So it's an incidence vector of an edge. So this matrix roughly takes us number of rows times log n bits to describe. So you don't need to lose this k squared over here. The k squared is in the completely general case. Any other questions? Yeah.
Theorem 2, you don't have the k squared. Theorem 1, you do. Is there a reason it should be?
Sorry?
Okay, never mind.
So this theorem is already expressing it in terms of how many of these rows do I need to measure. And these are theorems about linear functions from some space to some space when they're well defined. This is higher degree polynomials. They appear, but we won't really talk about them in this talk. Other questions? Yes, Kent.
Double check. So K, if we're doing cut sparsification, K is vertices and 2 to the K is vertices on one side of a cut.
Right. 2 to the K is the number of possible cuts. Exactly. Yeah. So the number of subsets of all the vertices, K would be the number of vertices for cut sparsification. Right. Yes.
Does it also imply a sparsification for directed graphs as well?
Does this imply a sparsification for directed graphs? No, it will not give you a nearly linear sparsification for directed graphs because that's not a linear function in this sense. You can get a sparsification to quadratic size by using degree 2 polynomials, but then that's not a sparsification really. I mean, every graph has only n squared edges. Yeah, but you can get some maybe hypergraph-ish sparsification results where n squared might be non-trivial, and those things follow from this here. Any other questions? All right, so more theorems before I start giving some proofs. These are theorems. How do these results translate to CSPs? I will not really dwell on them in the rest of the talk, but let me just tell you kinds of theorems that we are getting. For every ternary predicate on 3 variables, on 3 Boolean variables. So if you're thinking of a hypergraph query question on where all hyperedges have 3 things, but our notions of cut may be different than thing, but any question that you can ask, we can tell you exactly how well it is sparsifiable. And the question is basically just, yeah, you know, if this predicate was x should be 1 and y should be 1 and z should be 1, then there is no sparsification possible, n cubed is the trivial answer. But in other cases, there's something else. So it depends on what is the largest and that you can embed in this function. And that completely captures the sparsifiability. And this, so in particular, one interesting thing is if the predicate happened to be the XOR of 3 bits, then it's actually nearly linear sparsifiable. Okay. So this is, we can tell you exactly how well each one of these predicates is sparsifiable. This is a classification, but it's a classification for a finite set of functions. Okay, there's only so many functions on 3 variables. If you're looking for more sparsifications, if you have any symmetric predicate on Boolean variables for any number of variables R, and symmetric is pretty natural in the context of hypergraphs. I mean, you know, you permute the vertex names, it shouldn't affect whether the constraint is satisfied or not. So, so fairly reasonable consideration. For every symmetric function, CSP of P is nearly linearly size sparsifiable. If and only if this, you know, if you have a symmetric function, then you can say how many ones in the input assignment will satisfy it. And if the set of things which don't satisfy it form an arithmetic progression, then it's sparsifiable to nearly linear size. And that's an if and only if. Okay, so if it's not the case, then it requires at least quadratic size. Up to this point, it's exactly linear. It's a consequence of the linear sparsification. It requires linear sparsification over these integers and groups. And finally, if you just want non-trivial sparsification and your functions, you have a hypergraph with all constraints, all hyperedges having R variables, okay, every edge having R vertices, and you have some arbitrary predicate which says when an edge is cut and when it's not, then trivially this hypergraph has n to the R edges. So a non-trivial sparsification should be like n to the R minus 1 or less. And we can classify exactly when such non-trivial sparsification is possible. Okay. So these are all the things. And by the way, our initial results over here were all non-algorithmic, saying such sparsifications exist and such do not. In a later work, we were able to show that everything that we're getting here is actually algorithmic, which surprised even us for a little bit of time. All right, so those are the theorems. Now I'm going to translate to proofs. Questions? All right, so, I mean, I said I won't talk about graph sparsification, but Karger's algorithm and Karger's counting bound is crucial to our analysis and proofs as well. So I'll review that for starters and then come back to it. I'll do that a little bit fast because you've seen it all before. Most of you have seen it all before. So first, of course, you know, we are doing sparsification. The natural thing is, why don't we just pick a random subset of the edges? Let's just remember that we want multiplicative approximations. And so if a graph sort of looks like this, a random subset of the edges is never going to find this edge, and this edge is necessary to be able to answer the question of how many edges cross this cut. So if you want to answer every cut correctly, approximately, you have to include this edge. So we knew this, and this is why Karger said, okay, look, when we want to do this, we want to somehow make sure that the graph does not have too many small cuts like this, and then maybe we can be in business and let's go from there. So he proved this cut counting bound, and let's prove that cut counting bound for you. So the way the cut counting bound works, we want to count how many cuts are there with at most alpha times c edges, where c is the minimum cut in the graph. The way we will do this, prove that the number of such cuts is small, is by fixing a cut in our heads, running a random process which does not know the cut that's fixed in our head, and say this is going to end with the cut in our head with probability at least n to the minus alpha. If that happens, then the number of such cuts can be at most n to the alpha. So we fix the cut, and what we are going to do is repeatedly just pick a random edge in the graph and contract it. And the claim is that each time when we pick a random cut, it's not going to pick one of these edges from our small cut, because it's a small cut and there are lots of edges. And because there are lots of edges, it turns out that the probability that one of the edges from our cut is chosen at when we have like I edges left is at most 2 alpha over I. And then this miraculous identity which says the product of these quantities is basically n to the minus alpha. So if you know all this, then you kind of conclude that you cannot have too many cuts which have at most alpha c edges. The number of such cuts is at most n to the 2 alpha. Okay. So I'm going over this fast because kind of considered sort of known material, but there's like real cleverness in this analysis and very surprising conclusions. So one thing that I do want to talk about is how do you get sparsifiers from the cut counting bound? And the reason I'm going to go into this is we have a slightly different proof than Benczur Karger, and it may be kind of interesting and useful, and certainly in our case it's turning out to be useful. So first, if you have a graph in which you have a minimum cut of value c, and c is large, let's say you have a graph on n squared edges, and the minimum cut value is like n, omega of n, then it's trivial to go from the cut counting bound that we have to a sparsification result. You just randomly pick m over c edges, and m over c in our case is roughly n. And the probability that a small cut is not sampled well is small enough that it can overwhelm the union bound over the number of small cuts. And that's where you use the fact that the number of small cuts is small. So for each value of alpha, if there is a cut of size alpha c, the probability that it's not sampled well is maybe n to the minus 10 alpha. The number of such cuts is, on the other hand, at most n to the 2 alpha. So you can take a union bound over these, and now you sum it up over alpha, and you get every cut is sampled well. This doesn't work so well if your graph has got n squared edges and has a minimum cut of size 1, like in the example from before. And in order to do that, cover those cases, Benczur and Karger defined this notion of importance sampling and strength of an edge and so on. Here's a different way of getting this thing. It's going to get roughly linear, but not maybe loses further log factors. So imagine you're starting with a graph which has n squared edges, and we are going to target getting a sparsifier of size n to the 1.5 for the moment. And the way we will do it is the following. We'll just take all the graphs, so all the cuts which have at most square root of n edges crossing the cut, and take all of these edges. How many edges do you get this way? Well, at most n to the 3/2, because each time I take one of these cuts has square root of n edges, you split the graph into 2 pieces, and now you can't keep splitting the graph into 2 pieces more than n times. So n to the 1/2 edges are produced this way. N to the 1.5 edges are produced this way, and this will be some graph. And because I'm targeting a sampler of size n to the 1.5, this is completely acceptable. I can keep all of these edges around and say this is good. On the remaining graphs, these are all graphs which have minimum cut value at least square root of n. I can apply Karger's algorithm from here and get n to the 1.5 size samplers on all of those. Okay, so you put all of these together, you have n to the 1.5 edges, which has sparsified this original graph. You, of course, have to be careful when you see an edge from one of these samplers in your thing, you count it as square root of n edges, whereas when you see an edge from G0 crossing some cut, then you only count it as one edge. Okay? So the weighting is coming up naturally. But this is not the end of the story. Immediately you can recurse on both halves using the same formula, except we've just changed m and c and so on. Now you can set c equal to n to the 0.25, and further get four sparsification, which are all of this type. And so you can keep recursing this way. And at log n levels of recursion, you would get an n to the polylog n size sampler, which captured all the cuts. Okay, so it's the important sampling somehow comes up very naturally over here without explicitly defining notions of strength. And this is kind of useful for us also. All right, so now we'll turn to code sparsification. How do we extend these things? Before I tell you about code sparsification, I want to tell you why code sparsification should be hard. We've looked at this question of hypergraph sparsification before in the community and realized that, okay, this is a little bit more of a tricky question. So suppose I have a R uniform hypergraph, and the notion of the cut is the vanilla one. And a bipartition cuts an edge if there's at least one vertex on each side of this edge. Okay. Question is, are there nearly linear sized hypergraph sparsifiers? And this took a little while to work on. I think this is Roby's work, which says that there are sparsifiers of size O tilde NR. And then later, Sanjeev and collaborators found an improvement to O tilde of n. So yes, you can get sparsifiers of size nearly linear in this graph, but these were kind of, as far as I can tell, I mean, these are not direct things which sort of extend the Karger paradigm and apply it to this thing. It's a little bit more subtle than that. Oops, not that. So here's our proof, assuming we can sparsify codes. This is how we do it. We will work no longer over F2, but over some field FQ, where Q is larger than n and prime, so roughly of size n. Still the same notion. A code over a thing is given by a matrix that looks like this. We want to sparsify it, which means you'll pick a subset of the rows there. And what we will do is map an edge. Let's say there's an edge on vertices 1 through R. I will map it to the vector, which is 1, 1, 1, and in the last coordinate is minus R minus 1, and then the rest of them are zeros. Okay, so that would be the vector corresponding to a particular edge. And then I write down these vectors corresponding to all the edges. Okay, does this make sense? Now, if I look at a 0, 1 vector, which is the incidence vector of a cut, and multiply it with this row, the resulting quantity will be non-zero only if all the vertices are on one side, will be 0 if all the vertices are on one side of the cut, and it will be non-zero otherwise, because you cannot add some subset of these elements to each other and get a 0. That's it. Okay, so if you can do code sparsification, you can do hypergraph sparsification. So we have to do code sparsification over a large field, but yeah, I mean, as long as you can do the linear algebra there, then you're fine. Okay, does this make sense? All right, so if we had known that we were sort of looking at this hard problem, we might have probably lost faith, but fortunately, when we got a code sparsification result, we didn't know this reduction. So we just blundered ahead and got interesting results. So in order to prove code sparsification, we need an analog of the cut counting bound, saying, look, in every code of minimum distance d, this corresponds to the minimum cut. The number of code words of weight sort of constant times the minimum distance is at most polynomial in the length, in the dimension of the code. That's the kind of theorem we'd like. And this theorem is just patently false. Okay, the whole holy grail of coding theory is to design asymptotically good codes. Asymptotically good codes have d, which is omega of n. So a typical vector over here will be a typical column vector in this code will have omega of n non-zero values. How many code words have order of n non-zero values? All of them. And the number of such code words is exponential in n. That's our holy grail. I mean, so that's what we want anyway. So this is just completely false. But it's not so dismaying here. I mean, there's analogous statements that were known in the hypergraph setting, and these were considered sort of obstacles to a counting bound. But here it doesn't sound like an obstacle because it's not an obstacle to sparsification per se. If your code is asymptotically good, then just doing random sampling is going to work. We know this. Okay, so this is not really an obstacle. So how do we capture this fact that this is not a real problem and this is the only problem? So what we were able to show is that there's basically every code has a good coordinate, very good, asymptotically good code supported on few coordinates. Okay, if that's the case, then we should definitely store those few coordinates because there's a lot of code words sitting here. That's good for us. And the dimension of these code will pay for the thing. We are willing to pay as many coordinates as the dimension k. And if you have a very good code supported on a few coordinates, that's good. That takes away those dimensions and we can work with it. Or the code itself natively satisfies Karger's counting bound. So like the number of code words of weight, blah, 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 is so much. The formal lemma is stated this way. We have an additional parameter called t. We say, look, you can specify whatever integer t you want. Number of code words of weight at most alpha t is either like in Karger's bound, polynomial, or there is some very good code whose support is relatively small compared to the dimension, only t times larger, and this is a code. Yeah, it's a high dimensional code with small support. It's not asymptotically good, but it's just a small. It's supported on very few coordinates. And so those coordinates are important. You must sample them. Okay. So once you have this, so there's a corollary that you can, an alternate way of looking at it is every code has some important coordinates. And if you remove these important coordinates, on the rest of them, you satisfy the counting bound. So that's just an equivalent way of looking at this lemma. And it's maybe convenient way when you're doing applications. So, yeah, question.
Could it be that there are important coordinates?
If the code happens to have symmetries, then there will not be important coordinates, I think.
And then the Karger thing holds?
And then, yeah, that's a good point. Then probably just means that the Karger bound just holds, yeah. Okay, that's a great question. So there are lots of well-studied families of codes where no coordinate is any distinguishable from any other coordinate. If that's the case, my guess, I mean, it could be that there is a subset of coordinates which are together important, but I don't know. Okay, but my sense is it should just say that in those codes, in symmetric codes, the counting bound should just hold, period. Okay, that's my sense.
Violate the high rate somehow?
No, I think you can have asymptotically good codes which are they satisfy the counting bound, Karger counting. No, sorry. Okay, I'll have to think about this. Good question. I wasn't thinking like a coding theorist. Okay. So once you have this kind of a counting result, you can basically run through the same program as we did before. How do you sparsify a code? You apply this lemma. It says some coordinates are important, keep them, and others are not important, or there's a counting bound that holds their sample over there. Okay, and the analysis is pretty much the same as before, so I won't carry it out. Just a quick thing about how you do the code counting. How do you prove this code counting bound? It's actually very, very, very similar to the Karger analysis. The way we would think of it is in this graph, what you want to pick is a random coordinate which is not all zeros. So, I mean, if the code happens to be 0 on this coordinate for every code word, then there's no point, sampling that coordinate. So instead, what we're going to do is look at a coordinate which is not all zeros, and amongst all those coordinates, pick one uniformly. And what we're going to do is look at all the code words here, and if anybody is non-zero, you throw them away. Okay, throw away these things. So you get a sub code, which is also a linear code. And if you have a code word of small weight somewhere, it's very unlikely that it will be thrown away by the process in the same way as we had for Karger's bound, because the chance that you would choose this coordinate, which happens on which your code word happens to be non-zero, is small. It's there are n coordinates overall. Our code word is non-zero on t of them, or alpha t of them. The probability that you pick this, you throw away this code word is alpha t over n. Okay, and now you can just keep working your way through until at some point you get a code which is like where you find, oh look, everybody has large weight, nobody has small weight. At this stage, you stop and say, oh look, I found a large code as I want. Okay, I think it's roughly, did I get it? Louis is master of this proof, and if I'm wrong, then you should ask him questions. All right, so this proof methodology works. You get the counting bound, and once you have the counting bound, you can sparsify all codes. Once you can sparsify all codes, you can get pretty much all the results that we care about. By the way, how do you do all of this efficiently? So I give you this large matrix specifying the code. How do you find out this right submatrix, which is going to be a sparsifier and the right weighting? A priori, this proof roughly says, oh, look for these small weight code words in this code, and looking for small weight code words in a linear code is an NP-hard problem. So this approach is not going to work. And it did work in the minimum cut setting, because if you had looked at the code which was corresponding to the usual incidence matrix of a graph, a minimum weight code word is a minimum cut, and a minimum cut is a polynomial time solvable problem. But a minimum weight code word is not a polynomial time solvable problem. So for a while, we really thought this is not going to have a polynomial time solution. But fortunately, there is an alternate way of finding a sort of a sparsifier for a graph, which we can apply over here. And roughly what it says is, given this matrix, start peeling off full rank submatrices over here, okay, and keep doing that up to t times. And by now, if you had a code word of weight at most t, you would have found it, or you would have sampled all its coordinates. Okay. And this approach somehow allows us to, without being able to solve the minimum distance problem, solve the sparsification problem efficiently. Finds us a small subset of coordinates which includes all the important coordinates. So that's this algorithm, but never mind that. So a couple of implications. I don't know exactly what I have in mind. So let me, so like I said, oh yeah, this hypergraph sparsification. Whoops, did I repeat the slides? Sorry, never mind that. So we already talked about hypergraph sparsification, and my count is going to be off by 1 because I duplicated that slide. So we can just generalize this to more general functions, like I said, and it's not completely, the linear algebra breaks down because we are no longer in a linear algebraic space. It's a module and has its own complications. So it starts to put things closer to lattice, games that you would play with lattices. But thankfully, almost everything that you'd want to do works. You can't do Gaussian elimination, which is kind of central to this argument of eliminating code words which are, to the contraction argument, but instead you can use like the Hermite normal form of a lattice and work with that, and the machinery works. And this was kind of necessary in order to get this thing. So suppose I have a predicate which is symmetric on 12 variables, and it's satisfied at levels 1, 7. Okay, so this is like 1 modulo 6. So, okay, so this is something that should be sparsifiable in linear thing, but in order to sparsify it, we have to work on the group, which is G6 or something like that, with Z mod 6. And we need a theorem which says, oh, even when you're working with the group Z mod 6, you can actually sparsify. This theorem gives it to us with some work. And you can start specifying higher degree polynomials and still get very similar results, but now the sparsification that you get is dependent on the degree of the polynomial. The interesting thing is, okay, degrees of polynomials can only be integers. So that means the only sparsifications that we get are either of size n in an n vertex graph, or n squared, or n cubed, or n to the fourth, etc. Some n to the power of some integer, roughly, up to polylog factors. Nothing strictly in between. So there's no n to the 1.5 that we see. And that's not a theorem that there's no other such sparsifications existing, but these are the only, at this stage, this one thing, one theorem suffices to get all known CSP sparsification results. So as far as we are seeing, there's no sparsifications of size n to the 1.5. And it would be interesting to see what, if such a thing exists, or if we can formally rule it out. So like I said, this helps us classify all symmetric things. It also allows us to say that, look, if you have a Boolean CSP with on R uniform edges, then it'll have an n to the R minus 1-ish sparsification under some conditions, or else there's no non-trivial sparsification. So some open questions. I think the interesting thing is we have basically one upper bound tool, which is this polynomial-based sparsification. This is how the CSPs we can sparsify. There's one lower bound tool, which is saying, oh, somewhere inside there is an AND of t variables sitting in their constraint, and ANDs of t variables do not have sparsifications of size t n to the t minus 1. And these two don't really match. So we don't have an understanding of which of, so is there something else? Is there a new tool for proving lower bounds? Is there a new tool for proving upper bounds? We don't seem to have any ideas. So that's where we are, and thank you.
Any questions?
In the reduction to hypergraph sparsification, it sounds like you're still plugging in Boolean vectors, even though you're working over a larger field?
That's right, yeah. So notice that what we are interested in is to see which hyperedges cross a cut, and the cut is given by a Boolean vector, which vertices are on the left of the cut or the right of the cut.
So in the code sparsification, like you're looking at maps from fq to the k to fq to the n, but you're still only like plugging in Boolean vectors.
That's right, yeah. In the code sparsification, we only, well, okay, in the code sparsification results, we can actually plug in any values over here, but the values of interest to us in hypergraph sparsification is a subset. So that's one of the interesting things about this sparsification universe. If you can take a broader class of queries and sparsify that, that's only helping you with the subclass. Thanks, that's a good question. Nikhil?
So in your recursive cut sparsification algorithm, you repeatedly found small cuts and divided the graph. What is the analog of that in this setting?
So we repeatedly finding a subset of coordinates, which are kind of important in the sense that, yeah, there's a subcode supported only on this, a high dimensional subcode supported only on these guys. We remove those coordinates and say set them aside and then sparsify the rest. And then you can recurse again on both sides. Yes.
It sounds like the definition of sparsification here is not closed under complement. And the question is, can we imagine creating a sparsified and then post-processing the results from it to get the answer we want? So rather than sparsified directly approximating every cut, you do calculation something and then compute a function to get the cut value.
Right. So the complementation thing, I think it's a feature of multiplicative approximations. Okay. So just like we know that independent set sizes are not approximable, but vertex cover sizes are approximable, this is very similar. Okay. It's inherited because of similar reasons. There can be very, very tiny cuts under one definition of a cut, and then you negate it, and then suddenly every cut becomes large. Okay. And as far as being able to use one sparsifier to get results about others, I kind of don't remember having to use it somehow, but yeah.
Yes.
Sorry. is this something related to maybe the min-cut problems that use sparsifiers? And is it possible to have a better ground if, let's say, you only want to sparsify the codes which are of like low Hamming weight, and for the large ones you just somehow want to say that they are not small?
I see. So you don't want to answer the question, what is the approximate cut size for everything? You're sort of, there's a band where I haven't thought about that question before.
An identity matrix would still require like omega k.
Yeah, you're not going to compress.
I see. Okay. So just, yeah, I mean, okay, yeah. You cannot go sublinear in the number of vertices in some senses. Yeah.
So far you're looking at the sparsification and you wanted to get some, let's say, bit complexity, the first type of theorem. But if you care about bit complexity, does it make sense to look at the sketching and like left multiply by fat matrix, for instance, and see what that will give you?
Okay, so
It's kind of like Johnson-Linden stress type thing.
Yeah, for instance.
So we looked at this. I think a lot of these theorems use like real value analysis, and the weird thing here is that like we want to do like the weights are happening over the reals, but the actual inner product is happening over a finite field, and somehow we couldn't find any results that like work for this kind of mixed setting.
But is the setting make sense? Like for instance, what happens if I just left multiply by random 0, 1 matrix, or something like that? So.
I think, I mean, even when you left multiply, I mean, when you multiply by a random matrix, then you're typically expecting, so by the way, by left, I guess you want the matrix sitting here, right? And you're going to do real multiplication here and finite field multiplication there.
Or maybe both finite field. Just as a question, I'm not saying we can use JL or something.
Right.
As a model, does that?
As a model, multiplying by a finite field matrix over here, makes sense. We don't know that it will preserve, we don't know of theorems which will preserve distances. And in general, I don't know that we expect linear sketches, or at least I don't think we've been able to find linear sketching for code sparsification.
And also, if your question is about the bit complexity, so I think there's basically a quadratic lower bound actually due to Roby's work, because this captures the hypergraph setting, and we already know basically quadratic lower bounds in hypergraph settings.
Any more questions? Oh, one question.
Could there be a way to define spectral sparsification in this setting?
We thought about it quite a bit and haven't got anything interesting. No. Yeah. I mean, it would be very interesting because all of our things are off by several polylog factors here and there. And if you want the ultimate result matching the graph setting, the only way we get there is by spectral sparsification. So, yeah.
There is one more.
Yeah, so it seems like you're talking mostly about like the generator matrix here, but if you do that as a parity check matrix, then you're like, I guess, sparsifying the syndrome. So would this let you like de-randomize an LPC check or something?
Okay, I never thought about the random. I mean, I didn't think about what happens if you work with the parity check matrix over here. Sort of for the parity check matrix, we would be left multiplying it with some long vector and trying to see something about it. So I'm not sure what it would, but it's plausible that there's some sort of a, seems unlikely that we should be able to pre-commit to a subset of coordinates and say, I'll only look at those coordinates and measure the distance of a word from a code. So probably won't work, but I don't, yeah.
Okay. Done with questions. Let's thank Madhu again.
Yes.